officially attacked Oracle and Amazon data centers in the Mideast.
Amazon could be facing outages because of airstrikes happening across the Middle East.
They completely change the way you think about data centers and redundancy and critical thinking.
In the UAE was down after Iranian drones hit the UAE data center. This is a developing story.
Exposed to a category of risk the data center industry was never primarily designed around. It forces us to rethink one of the most influential frameworks ever designed for data centers.
Amazon said Monday its cloud computing facilities in the Middle East face power and connectivity issues after what it called unidentified objects struck its data center in the United Arab Emirates.
So a few weeks ago, something happened that should make every data center operator and cloud architect and investor and infrastructure strategist pause. Not because a server failed, or not because a generator didn't start, not because a cooling system went offline, but because cloud infrastructure itself became part of the conflict map. So on March 1st, 2026, reports emerged that Amazon Web Services data center facilities in the UAE and Bahrain had been damaged by drone strikes and missile hits. Then on April 1st, Reuters reported that Amazon's cloud operation in Bahrain had been damaged after an Iranian strike, citing the Financial Times. So think about this for a moment. One of the most sophisticated technology companies on earth, operating some of the most redundant infrastructure ever built, still exposed to a category of risk the traditional data center industry was never primarily designed around. Intentional physical disruption. So for decades, we have asked one question. Can the data center survive failure? Power failure, cooling failure, network failure, equipment failure, maintenance events, human error. And modern data centers became extraordinarily good at answering that question. But the question is changing because in the age of artificial intelligence, cloud platforms, geopolitical tension, drone warfare, and strategic compute, the question is no longer only can the facility survive failure. The new question is, can the facility continue operating when it becomes a target? The difference may define the next era of data center design, because a facility can be highly redundant and highly available and still strategically vulnerable. Now that blind spot is what this video is about, and we call it the survivability gap. And before we continue, if you enjoy deep dives into infrastructure, artificial intelligence, resilience engineering, and the hidden systems shaping the modern world, consider subscribing. This channel is going to explore a lot more of these topics in detail. Now, before we jump in, a quick note. This is not one of those videos that you watch while scrolling in the background on your phone. There is a lot of information packed into this discussion, and some of the ideas we're going to cover. So if you are serious about this topic, grab a notebook, take a few notes as we go, and very importantly, make sure to download the free resource briefing linked below. It summarizes the key concepts and diagrams and frameworks we'll be discussing, and will make it a lot easier to follow along. Alright, let's get started. Now, to understand why survivability matters, we first need to understand how important data centers have become. Now, 20 years ago, most computing was relatively distributed. Companies often operated their own server rooms and applications were smaller, and infrastructure demand was a lot lower. But cloud computing changed everything. And so instead of thousands of small isolated systems, computing began concentrating into massive hyperscale facilities. And then artificial intelligence accelerated this trend dramatically. So modern AI systems require enormous computational density. That means thousands of GPUs and massive networking capacity, immense cooling infrastructure, gigantic power delivery systems. And this created a new type of strategic infrastructure that we call strategic compute. And so today, a single hyperscale AI campus may contain enough computational capability to support national scale AI workloads and financial systems and cloud services and enterprise platforms and massive portions of the internet economy. Which means uptime is no longer simply an IT problem. It is now an economic problem and a societal problem, and potentially, and this is very important to understand, even a geopolitical problem. Which is why the data industry became obsessed with resilience. Now, as data centers became increasingly critical, the industry developed sophisticated ways to eliminate downtime. And one of the most influential frameworks came from the Uptime Institute. And we call this, or rather they call this, the tier system. Now, before we continue, this is important. The tier system is not bad. I'm not saying this at all. In fact, modern Tier 3 and Tier 4 facilities are among the most operationally resilient buildings ever constructed, designed to solve a very specific category of problems, operational failures. Now let's quickly break this down. So Tier 1 facilities are relatively simple, minimal redundancy, single power paths, limited fault tolerance, and if maintenance needs to happen, systems may need to shut down. Tier 2 introduces redundant components, backup generators, UPS systems, additional cooling capacity, but most of the infrastructure still depends on single distribution pathways. Tier 3 becomes significantly more sophisticated, so infrastructure becomes concurrently maintainable, meaning major systems can be serviced without shutting the facility down. And this is where we begin seeing dual power paths and multiple cooling systems and advanced electrical redundancy and far more operational flexibility. Then comes Tier 4. Now, the highest traditional level of fault tolerance is what we call Tier 4. So multiple active power paths, multiple cooling paths, extensive redundancy, the ability to survive multiple simultaneous operational failures. And these facilities are engineering masterpieces. And also, as you may think, it's very expensive to run a Tier 4 and to build a Tier 4 data center. And when you walk through a modern hyperscale campus, you immediately notice the scale of this resilience. Redundant substations, multiple generators, massive UPS halls, battery systems, backup fuel infrastructure, redundant cooling loops, diverse network connectivity. Entire systems duplicated again and again to eliminate single points of failure. And for decades, this philosophy worked extremely well because most failures were accidental. Utility outages, equipment failures, cooling system breakdowns, and even human operational mistakes. The industry became incredibly good at handling those problems. But there's an important detail hidden inside this entire philosophy. The surrounding environment was assumed to remain relatively stable. And that assumption may no longer hold. So, in March 2026, reports emerged of drone and missile activity affecting cloud and infrastructure facilities connected to Gulf region AI and hyperscale operations. While the operational details remain heavily debated, the psychological impact inside the infrastructure industry was immediate. This I can assure you of. Because for perhaps the first time, many people began asking, what happens if modern cloud infrastructure becomes part of the threat landscape itself? The global infrastructure landscape has changed dramatically over the past decade. And this is one of the most important parts of this discussion. Historically, threatening critical infrastructure required enormous capability. State-level militaries, large-scale sabotage operations, complex attack coordination. But modern technology changed that equation. Commercial drones are now inexpensive and precise and scalable and globally available. At the same time, modern infrastructure became increasingly visible and concentrated. You're not going to hide a hyperscale data center. Everybody knows where it is. So open source satellite imagery now reveals enormous amounts of infrastructure detail. They reveal the cooling systems, exactly where these are, transformer yards, generator farms, substations, fiber routes even, rooftop thermal systems. And this creates a very strange asymmetry. Infrastructure worth billions of dollars may now face threats costing only thousands. Now, to be clear, this is not about fear-mongering, and it's not about claiming that data centers are defenseless. They are not. The point is something much more subtle. The threat model changed faster than infrastructure philosophy did, and we've already seen versions of this problem emerge globally. Energy infrastructure attacks, telecommunication disruption, undersea cable incidents, cyber physical attacks, strategic infrastructure targeting. Because increasingly, modern conflict is no longer only about territory. It's about systems. It's about power systems. It's about communication systems, compute systems. And as artificial intelligence grows, compute infrastructure may become strategically important in entirely new ways. Because AI infrastructure is fundamentally different from traditional enterprise computing. AI workloads prefer scale. Massive centralized clusters, huge power densities, enormous networking fabrics, thousands of GPUs operating together. Which means modern AI infrastructure is becoming increasingly concentrated. And concentration creates a difficult survivability question. What happens when strategically important infrastructure becomes physically concentrated infrastructure? And this is where we arrive at the survivability gap. Now, you've heard me mention this a few times, but what exactly is the survivability gap? Well, the survivability gap is the difference between infrastructure designed for operational reliability and infrastructure capable of continuing operation under deliberate attack. And this distinction changes everything, because redundancy and survivability are not the same thing. Redundancy assumes randomness. A component fails unexpectedly, or a utility feed goes down, or a cooling unit stops operating. So systems are duplicated. And this works extremely well. But survivability engineering assumes something very different. It assumes intentional disruption. And intentional disruption changes the design logic completely. So let's look at a few examples of this. Modern hyperscale facilities often place large portions of their cooling infrastructure externally. Cooling towers, chillers, condenser systems, heat rejection systems. These are frequently visible from aerial imagery. Now, operationally, this makes perfect sense. Large cooling systems require airflow, maintenance access, and physical scale. But survivability engineering asks a different question. What happens if thermal infrastructure becomes the target? Because here's something many people outside the industry don't realize. You don't necessarily need to destroy servers to disable a data center. Thermal disruption alone can force compute shutdowns. Modern AI clusters generate extraordinary amounts of heat. And a modern AI GPU can consume hundreds of watts by itself. Now multiply that across thousands or tens of thousands, even hundreds of thousands of GPUs operating simultaneously. And these facilities effectively become giant heat generating machines. Which means cooling is not a secondary system. Cooling is compute continuity. And if heat rejection systems fail for extended periods, workloads may need to throttle or shut down entirely to protect hardware. And the same logic applies elsewhere. Transformer yards, fuel systems, substations, fiber ingress pathways, network concentration points. Many facilities possess enormous internal redundancy while still relying on relatively exposed external infrastructure. Even network diversity can become more complicated than it first appears. Two providers may appear fully redundant on paper, while still entering the region through geographically similar pathways before diverging deeper inside the campus. So operationally, this works extremely well for reliability. But survivability engineering asks a different question. What happens if disruption is intentional? And this becomes especially important as hyperscale infrastructure grows larger, because modern infrastructure increasingly optimizes for efficiency and scale and centralization and density. But those same characteristics may also increase strategic vulnerability, which creates an uncomfortable but important realization. A facility can possess extremely high operational resilience, while still possessing relatively low survivability under certain threat conditions. And that is the survivability gap. So what we're discussing here is really only the introduction to a much larger framework. And in the full survivability engineering analysis, the discussion expands into distributed resilience and compartmentalized infrastructure and passive hardening concepts and strategic compute classification and rooftop segmentation, graceful degradation models and potential future infrastructure standards beyond traditional uptime philosophy. So I'll link the full executive ebook below for those interested in exploring the deeper engineering framework. But also remember that there is a free version that I will also link to for you. And I would actually prefer it if you upload the free version first. There will be links to the paid version in the ebook, the more expanded version. But have a look at the free version and let me know what you think about that. We really need conversations around this. Now, this does not mean the solution is turning every data center into a military bunker. Heavens no. That would be economically unrealistic in most cases, right? And it would fundamentally misunderstand the problem. The real question is not how do we make infrastructure invulnerable? Because true invulnerability is simply impossible. The real question is how do we maintain continuity under disruption? And that leads to survivability engineering, which may involve things like greater compartmentalization and distributed compute architectures and regional workload dispersion, passive infrastructure protection, segmented rooftop systems that I've already mentioned, distributed thermal infrastructure, reduced concentration dependency, graceful degradation models, and importantly, designing systems to continue operating partially instead of failing completely. Because survivability is often not binary. It's about maintaining critical function long enough to preserve continuity. And this may eventually require entirely new ways of thinking about infrastructure classification. Not simply how much redundancy exists, but also how resilient is this infrastructure under intentional disruption. And this is where concepts like strategic resilience tiers begin emerging. This is frameworks designed not only around uptime, but around survivability itself. So, let's wrap this up. For decades, the data center industry focused on one central question. How do we prevent downtime? And in many ways, modern infrastructure became extraordinarily successful at solving that problem. But artificial intelligence is changing the scale and strategic importance of compute infrastructure. And the surrounding threat environment is evolving alongside it, which means the next generation of infrastructure questions may become very, very different. Not simply how do we survive accidental failure, but how do we continue operating when disruption itself becomes intentional? Because the future of infrastructure may no longer depend only on redundancy, but on survivability. Now, this video only introduces the concept of the survivability gap, but the deeper question may be far larger. What happens when AI infrastructure becomes strategic infrastructure? And how should the next generation of data centers be designed in a world where continuity itself becomes a security problem? Now, if you'd like to explore this topic further, I've linked both the free executive briefing and the full survivability engineering framework below, including a proposed new infrastructure classification designed specifically around survivability and continuity under deliberate disruption. Now, this is a concept I believe may become increasingly important in the age of strategic AI infrastructure, and I genuinely like to hear your thoughts. Do you believe the current tier system is enough for the world we are entering? Or do critical AI infrastructure and cloud facilities require an entirely new survivability philosophy? Please let me know in the comments. And thanks for watching.